All right, so I'm recording now. I'm going to share my note screen and we're going to finish up these partial derivatives. We know most everything there is to know about partials from last time, but we only talked about the first partials. Remember in chapter 12, we introduced the second derivative. And in normal cases, so let's recall from just like chapter 11 and 12 stuff. I gave you a function f of x, and you could find the first derivative. But you could also find the second derivative. So you could go through the first derivative and get to the second derivative. Remember, the way we did that was we just took the derivative of the first derivative and got to the second. So that was the flow. There was only one direction you could go, through the first to the second. And remember, you could go on beyond that, but we usually stopped at the second. In chapter 14, with these partials, it's similar, but remember, our first derivatives, we actually have two of them. So we're going to have options, or let's call them paths or something. You guys, so I'm going to make it, and I'm going to write these in the F notation for this little chart I'm going to make just because it's easier, and then we'll be reminded of the other notations as we go. But you guys, so we start with f of xy. So we start with our original function. And as far as the first derivative goes, we could take it with respect to x or with respect to y. So if I wanted to take a second derivative, well, I could take the first with respect to x and then take the derivative of this again with respect to x. So notice this notates a second order partial is what we call it, a second order partial derivative, where the first derivative we took with respect to x, and the second I also took with respect to x. So we call it fxx. But from that first derivative with respect to x, what if the second time I took it with respect to y? I could do that, you guys, because I have options. I have two input variables. And the same with y. So maybe I started with y, and I took it again with respect to y and got fyy for my second partial. Or maybe I took it with respect to y, and then the second time I took it with respect to x. So the order matters which way we go, you guys. So notice, because I have two first derivatives, I now have four second derivatives. And we're going to be finding all of those. So let me give you a function, and we're going to do a lot of things with this function. So I'm going to make it kind of long, make sure it involves everything I want it to involve. So let's say that our function f of xy equals 3x squared y squared plus 2xy cubed minus 4xy plus 5 x cubed y to the fourth minus 7x plus 8y. I'm not going to put constants on it. But yeah, so long function. And I want to find, so I'm going to say I want to find all first and second order partials, which means all 6 of those, the 2 firsts and the 4 seconds. And I'm going to write these. So remember, notation for partials, we have this F notation, but then we also have the fraction notation. So you guys, I'm going to start with the derivative with respect to x. Remember, we could write it like this. And in your homework, some of your questions, remember how we talked about when we have an input x and y, we call the output z. Sometimes if we're not in function notation, we just call it z. Some of your functions in your homework are like that. They just call them z. So when they ask for the partial, it might say something like this, dz dx. But note that this f and this z are the same. It's just one is in function notation and one is just not. So if you see a dz in your problem, don't let that throw you. It's the same thing as df. What's the other way we could write this? Well, just fx. All right, so let's find the partial with respect to x of this fxy, f of xy. So with respect to x, you guys, the 3 and the y squared are coefficients of the x squared. And then for the x squared, I do the power rule. This one, the 2 and the y cubed are just coefficients. And because this was x to the first, only the coefficients come down. Minus, you guys, again, with the x to the first here, it's just going to be the 4 and the y coming down. This one, 5 and y to the fourth come down as coefficients. And then I do the power rule on the x cubed. I'll get minus 7 for this minus 7x. And then the plus 8y doesn't have an x in it, so it just goes away. So let's clean this up. We've got 6xy squared plus 2y cubed minus 4y plus 5, let's call this plus 15x squared y to the fourth minus 7. So we did a lot of this last time. And you guys, before we move on from that, just because we can, I want you to find fx of 1, 2. So you're going to have some where you evaluate derivatives at certain points today, so I want to make sure you can do that also. So notice this is the first partial, just fx with respect to x. And once you find it, you can put in a 1 for the x and a 2 for the y. Just make sure you find the partial first and then put this point in. So what would that be? It'd be 6 times 1 times 2 squared plus 2 times 2 cubed minus 4 times 2 plus 15 times 1 squared times 2 to the fourth minus 7. So a lot of things happening here. This is 6 times 4, so we get 24. 2 cubed is 8 times 2 is 16 minus 8 plus 15 times 16 to 40, maybe, hopefully. If I'm wrong on that, somebody yell at me about it. I think it's 240 though. Okay, so, and then you guys, so we'll just add and subtract these. So we have 24 plus 16 minus 8 plus 240 minus 7. So 265, I think. Yeah, or I said 5 and I wrote 4. I don't know why, guys. Who knows? But something like this. You guys, so basically, I just want to make sure that if it wants you to evaluate a derivative at a point that you can do that. You find the partial it's asking for and then put the point in. But let's move on from that. You guys, I have fx. Let's find fy. So what different ways could it ask me for this? It could say df dy like this. It could say dz dy, meaning the same thing, just not in function notation. Or it could just say fy like this. Either way, remember you're going to your original function and this time taking it with respect to y. So with respect to y, the 3x squared is all coefficient. And then you do the power rule on the y squared. With respect to y, 2x is a coefficient and you do the power rule on the y cubed. Minus 4x, 4x would be the coefficient on y, plus 5x cubed, that's all the coefficient, and then you do the power rule on the y to the fourth. And then the only thing left would be a plus 8 from that plus 8y. So let's clean this up. We'll get 6x squared y plus 6xy squared minus 4x plus 20x cubed y cubed plus 8. So I'm not going to have us evaluate fy at a point, but you know it would be the same as we did up here if we needed to. So we have fx and we have fy. Those are the two first order partials. I want to find the second order partials now. So what I want to start with is fxx, which means I'm going to look at fx and take the derivative of that again with respect to x. Here's other ways you might see this. In the fraction notation, second order partials have these 2's in different places. They look like squares. So let me you know, say this in words. This is the second partial of f with respect to x both times. It would look the same with the z, just with a z there. But either way, we need to go from our fx line. We took it here first. Now we're going to take the derivative of, well, not that one, because that one we put the point in. This is our simplified f of x, not f of x. We're going to take the derivative of this first order partial, again, with respect to x. So I can see that here, it's circled. Okay, with respect to x, 6 and the y squared are coefficients on this x, so those come down. The 2y cubed goes away because it doesn't have an x in it. The same with this minus 4y. Now, this term here, with respect to x, the 15 and the y to the fourth are coefficients. Then I'll do the power rule on the x. So I end up with 6y squared plus 30xy to the fourth. So there's fxx. Let's find fyy. So what would that look like? Well, it might just look like fyy. Or it might look like the second order partial of x with respect to y both times. Same thing with the z. I want to make sure you guys don't get confused when you see different kinds of notation. All right, so this time we're going to go from fy, which is right here, take the derivative again with respect to y. So with respect to y, 6x squared comes down as the coefficient. This time the 6x comes down, then I do the power rule on the y squared. That minus 4x goes away because there's no y's in it. The coefficient on y here is 20x cubed, and then I do the power rule on the y term, and then the plus 8 goes away. So we end up with 6x squared plus 12xy plus 60x cubed y squared. So we just found our first second order partials. We found xx and yy, but remember there's two more. You guys, now I need to do xy. So the first time with x, the second time with y. How does this look in notation? It looks like the second partial of f with respect to x, then with respect to y. Notice that this x came first. It's to the left, so it means x first, then y. And with the dz, it would look the same. On the bottom, it would say dx dy. But it does mean I have to go back up to fx and now take this again with respect to y this time. So the first time I did it with x, now I'm going to do it with y. So I might need to bring this down so we can see it, because yeah, I can't get everything in the one screen. So I have 6xy squared. I'm going to put it right here. Plus, too far. Okay. I didn't do any of those things. All that scrolling and stuff, that was not me. I don't know, guys. I'm about to lose my mind. Okay, so I had 6xy squared plus 2y cubed. Now I've already forgotten because my computer's going crazy. Minus 4y plus 15x squared y to the fourth. Then I think that last number was a constant, wasn't it? Minus 7, yeah. Okay, so it took forever, but I have the reference of fx down here now. So I can take fxy. So derivative of this function with respect to y this time. So with respect to y, 6x is a coefficient, then I do the power rule on the y squared. With respect to y, this term becomes 6y squared. This is going to be minus 4 This is going to be 15x squared coming down as a coefficient. Then I do the power rule on the y to the fourth term. And then that's it. Okay, so let's clean this up a little bit. I end up with 12xy plus 6y squared. I'm going to put that minus 4 at the back. Let's do plus 5. No, we're going to add those or multiply the 15 and the 4. So get plus 60x squared y cubed, and then let's put that minus 4 at the back. Okay, so there's fxy. Let's find fyx. So what would that look like? It could look like the second partial of x with respect to y, then x. Or it could look like that same thing with a z. Remember, dy and then dx on the bottom means that we did y first and then x. So you guys, I have to go back to fy, which I think I can fit that in the screen. This is fy right there at the top, that 6x squared y one. And then I'm going to take this a second time, but this time with respect to x. So with respect to x, let's see. The 6 and the y are coefficients, and then I do the power rule on the x squared term. The next term, the 6xy squared, I'm going with respect to x, so I bring down a 6y squared as the coefficients on that x. That minus 4x becomes a minus 4. 20x cubed y cubed. So here, you guys, we're going to get the 20 and the y cubed as coefficients. And then I'm going to do the power rule on the x cubed and get 3x squared. And then that plus 8 goes away. So let's clean this up. You guys, what I get is 12xy plus 6y squared. I'll put that 4 in the back. You guys, this term, the 20 times 3, I'm going to get plus 60x squared y cubed and then minus 4. Where have I seen that before? Well, notice that fyx and fxy are exactly the same. You guys, every single function you do, these will be exactly the same. Most functions work out this way to where fxy and fyx are always the same. There's barely any functions that don't, and definitely not functions that we're going to look at in this class. So that's something you can remember as you're finding first and second order partials when you have to. That would be a good check. If you have to find both xy and yx, it might be good to check that you got the same answer on both of those. One thing I wouldn't do is take that for granted. So let's say you find fxy and you're just like, okay, and that's yx too, and you put it in for both. Well, what if you were wrong on xy and then you're wrong on 2 of them? I would find both of them and just make sure that they're equal. That way you know they're correct. Let's see. So that was fun. That was a really long function. The next one's not going to be so long. This one's going to be exponential though. Let's say I've just got 5e to the xy. That's not too bad. You guys, I want to take first and second order partials. So let's start with fx because we usually do. So fx, with respect to x, I bring this 5 down. Remember the e to the xy also comes down as is, and then I do the chain rule. The chain rule, the derivative of xy with respect to x is just the coefficient, which is y. So fx equals 5y e to the xy. Let's go ahead and find fy, get the first order partials out of the way. So fy equals, well, the 5 comes down, the e to the xy also comes down. The only difference here is the chain rule with respect to y brings down an x as the coefficient on y. So I end up with 5x e to the xy. All right, so let's find some second order stuff. Let's do fxx. Okay, so I'm going to look at this and take it again with respect to x. So you guys, the thing is, it kind of looks like it should be a product rule, right? With the 5y and then the e to the xy. But with respect to x, y is just a number, right? So you can bring the 5y down just as a coefficient. And then the e to the xy comes down as is, and then you do the chain rule on this with respect to x, which just gives you another y. So we end up with 5y squared e to the xy. So that wasn't too bad. Being able to hold that y constant was really helpful. On this side, let's do fyy. Okay, so with respect to y, again, you guys, this x is now a constant, so it can just be a coefficient that comes down. No product rule necessary. So we bring down the coefficient, we bring down the exponential term exactly as is, like usual. Then when we do the chain rule, derivative of xy with respect to y is just x. You can see the similarities in these two just with the variable changing. This is 5x squared, e to the xy. My pen is really lagging. I'm not sure why. Okay, so I have xx and yy. Now I need to find xy and yx. These are going to be a little bit more involved. And we'll see why here in a second. So fxy. So remember, you're going from, well, let's go from this line, this 5y e to the xy. That's the first order with respect to x. I need to do it again with respect to y. Now, because I'm with respect to y now, this y is no longer just a coefficient. This is the variable I'm using. I can't hold it constant, so this is product rule. You guys, so for this fxy, I need u's and v's. So you guys, I'm going to say u is 5y, v can be e to the xy. So remember, we're going with respect to y, so du is just 5. dv is going to be e to the xy. Remember, with respect to y, we bring down the x as the derivative of xy. So we can just call it xe to the xy. Okay, so u times the derivative of v, which was xe to the xy, plus v, which is e to the xy, times the derivative of u, which is 5. We can clean it up maybe a little bit. I could call it 5xy e to the xy plus 5 e to the xy. And sure, you might be able to factor out a 5e to the xy, but it's not going to make it look any better. So I would just leave it like that. Okay, so there's f of xy. Now I know I should get the same value for fyx. So let's see what we get here. All right, so fyx, we're going from fy, which is this one up here, the 5x e to the xy. And this time we're going to take it with respect to x. So with respect to x, this is product rule again, right? I can't say that this x is constant anymore. So I need u's and v's. So let's say u is 5x. du would be 5. Remember, I'm with respect to x on this time. v is the e to the xy. And dv, this time with respect to x, it's e to the xy times y. Because remember, with respect to x, the coefficient comes down and it's just a y. So this time I get y e to the xy for dv. Let's put it together. You guys, so I have u times dv, which is y e to the xy, plus, sorry, v, which is e to the xy, times du, which is just 5. So it's exactly what happened over here, right? I end up with 5xy e to the xy plus 5 e to the xy. And they are exactly the same. But anyway, instead of just using that to say, oh, well, yx is that too, I went ahead and I found it, right? And that's what I want you to do. Because if we somehow got yx and it was not the same, then one of them would definitely be wrong, right? So I would need to go back. It's a great way to make sure you're getting the correct answers on all of them. So that was fun. We're going to just do one more. We need to look at a natural log. All right, so let's say that f of xy equals the natural log of, actually, you guys, I'm going to put this in absolute values, and I'll tell you why in a minute. X plus 2y. Now, you have a homework question, or there might even be two, where it's natural log, and they put it in absolute values, because sometimes we do, just to make sure that, hey, whatever x and y is, we know that natural log has to be taken positive. So I know that the argument of a natural log has to be positive. So sometimes when they write natural logs, they just put absolute values. Now, that's the reasoning behind it. But the thing is, it doesn't change anything about the derivative. And honestly, once we get rid of the natural log statement, so when we take the derivative and we don't have the ln anymore, you're not even going to have to use those. So when you see those, just treat them like they're normal parentheses. You guys, it doesn't change the problem at all. So don't let it throw you. Let's find fx. All right, so the natural log of x plus 2y, when I take the derivative, I get 1 over x plus 2y. See, already I'm not in a natural log statement, so I don't need any bars. And then remember chain rule. You guys, I need to take the derivative of this with respect to x, which is just 1. So fx is really just 1 over x plus 2y. Let's find fy. All right, so from the beginning, the natural log of x plus 2y comes down as 1 over x plus 2y. This time the chain rule is a little different though, because I have to take this with respect to y. So the derivative there is 2. So now I have 2 over x plus 2y as fyy, or just fy. All right, so I found my two first order partials. Let's go ahead and find some second orders. Let's start with xx. All right, so I need to take fx, which is right here, again with respect to x. Now, the way this looks, it's a quotient. It's got x in the bottom. I don't want you to go toward the quotient rule here. You guys, we haven't used the quotient rule in forever, and it's a good reason because usually we can avoid it. So when I see this, the first thing I'm going to do is just rewrite it. Can't I write this as x plus 2y to the negative 1? I know how to use negative exponents to rewrite stuff. So that's what I'm going to do here. And I'm just going to use the power rule with a little chain in there. So all I did here was rewrite fx. Now I'm going to take the derivative of fx again with respect to x. So this negative 1 is going to come down in front. I'm going to get negative 1 times x plus 2y to the negative 2. Remember how you have to do the power rule around the parentheses. And then you take the derivative of what's in here with respect to x, which is just 1. So what do we end up here? We get negative 1 times x plus 2y to the negative 2. You could alternately write this as negative 1 over x plus 2y squared, but I don't see a reason. You guys, this is just fine. But you could write it either way. If you like the fractions, if you like the negative exponents, it's whatever you like. MATLAB should take it both ways. So this is fxx. Let's find fyy. So taking this, let's rewrite this. You guys, it would have a 2 out front, remember, because this 2 here. In here, you could have x plus 2y to the negative 2 as the rewrite. Or sorry, negative 1, just like the first one. It doesn't have a power on it down there. So you guys, I rewrote fy just like I rewrote fx. It was a little bit different because this one had a 1 on top, so there would be like a 1 there. This one, there's a 2 in front. But I want to take the derivative of this with respect to y, so let's do that. That 2 is a coefficient, it comes down, but I also bring a negative 1 down. Remember, anything that's in these parentheses, it always comes down as is. I do the power rule around it. And then I do chain rule. I multiply by the derivative of what's in here. With respect to y, that's just a 2. So I end up with -4 times x plus 2y to the -2. Remember, I could write that as -4 over x plus 2y squared. If you wanted to write it like that, that would be fine too. But either way, that's what it would be. So there's my first two second order partials. Let's find the last two. Let's find fxy. So remember how to find that. I'm going to take this is fx. I'm going to take the derivative of this again with respect to y. So let's do that. The -1 is going to come down in front. I have this x plus 2y to the -2. Chain rule, take the derivative of this with respect to y this time is a 2. So what do I end up with? -2 times x plus 2y to the -2. Fyx. Well, let's see. So fyx, I'm going from fy, which is right here in the rewrite. So the 2 comes down, the -1 comes down in front. I do x plus 2y to the -2. So I do the power rule around the parentheses. Remember, I'm going with respect to x this time. So the derivative of x plus 2y just with respect to x is just 1. And I end up with the exact same thing I just got over on the other side. And we can see xy, yx, they're the same exact thing. So I feel confident that I did the rest of them correctly. So there's a lot of partials, a lot of keeping track of stuff. What am I taking it with respect to this time? Did I do x first and then y? You just have to be careful. It's all about details. And remembering when you're holding something constant, remember to hold it constant. These are easy to make a small mistake that make big differences. You're going to see in your homework, for 14.2, there's quite a few questions. I want to say there's 14. But there's a reason for that, you guys. This takes practice so you can get comfortable and not make tiny mistakes. So like I said, that homework is up right now. And then I'll see you Wednesday. Now, you'll probably get an email from me about how the rest of the class is going to go because, not all of us are here, obviously. And I talked about a lot of things. So I'm going to attempt to write it all down. It's kind of hard to explain what I'm doing, but I'm going to do my best to make it in simple terms. So I'll be sending that out, and I will see you guys on Wednesday.